that detect the missile. Okay. So just to clarify, the probability of a detection is 0.9. The probability of a failure is 0.1 for each satellite. I'm going to write down the outcomes associated with this. Okay. So my outcome variable is x here. Ultimately, I like to know p of x. And there's an event in the sample space associated with x. So possible values are 0, 1, 2, 3, or 4. So 0 means that no satellites detect the missile. That is, we have a failure, a failure, a failure, and another failure. When x is 1, that means I have a failure, and I need a success. So I made the last one a success. But it doesn't have to be the last one that's a success. I could have the second one be a success. I could have it be the second outcome. Or I could have success, failure, failure, failure. Okay. Those are all outcomes associated with x equals 1. For x equals 2, I could have failure, failure, success, success. Or I could have failure, success, failure, success. Or here's another way to have two successes. Success, failure, failure, success. And here's yet another way. Failure, success, success, failure. And I could have success, failure, success, failure. And here's the last way in which it could occur. I could have success, success, failure, success. Those are all the ways in which I could have two successes. Now, if I was to do x equals 3, I would just work it out similarly, and I'd get success, 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 failure, success, success, failure, success, success, failure, success, success, or failure, success, success, and success. Okay. And for 4, that would be the most desirable outcome. Every single satellite detects it. Now, I just want to point out here that here there was one way to have all failures. And notice we're not distinguishing between a failure that's colored red or a failure that's colored blue. It doesn't matter what color or distinguishes the failure. All that matters is the outcome is failure. So permuting these 4 failures does not change the outcome or the event. Similarly, if I was to distinguish this failure from this failure, well, I wouldn't really care about that. It's the same outcome. So what I'm telling you is it's not the order in which the failures or the successes occur is just the total number. So here's going to be 4 of them. here's going to be 6, here's going to be 3, and here's going to be 1. All that I care about when I'm figuring out and placing these failures is how many of them are there out of 4. Okay? So in general, what this is leading to us is that this 1, I'm placing no successes. This is 4, choose 0. This number 4 comes from 4, and I'm placing 1 success. 6, this is the same as 4, choose 2. This 3 is the same as 4, choose 3. And this 1, that's 4, choose 4. Okay? So the number of ways that this occurs is a combination, because distinguishing the failures leads to the same outcome. I don't actually care about distinguishing those. Okay. Now let's do a calculation of probability. And let's do this. I'm going to do probability x equals 3 successes. Well, that's going to be the probability of failure, success, 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 or success, failure, success, success, or success, success, failure, success, or success, 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 and failure. And because of this or right here and right here, I'm just going to add these. This is going to be probability of failure. The first is failure. The second is success. The third is success. And the fourth is success. Plus probability of success, failure, success, success. Plus probability of success, success, failure, success. Plus probability of success, success, failure. And really, this event right here is the first is success, the second is success, the third is success, and the fourth is failure. Using independence, the probability of failure is 0.1 times 0.9 times 0.9 times 0.9. If I look at the probability of success, failure, success, success, that again is going to be 0.1 times 0.1 times 0.9 cubed, 3 successes, plus 0.1 times 0.9 cubed, plus 0.1 times 0.9 cubed. If I look at this, I have 4 of the same object. So this is 4 times 0.1 times 0.9. Let's write this down just one more time and figure out what's going on. That 4, that looks like the number of trials. 4, choose 3. That's how I got that 4. Times 0.1, that's probability of failure. That's 1 minus p. Times p to the third. Okay. And really, I think this 1 minus p, that's 4 minus 3. So in general, for a binomial distribution, I think I have probability x having k successes is going to be n, where n is equal to number of trials, which is 4 satellites. We're going to have n choose k times 1 minus p to the n minus k, 4 minus 3, times p to the k. So in this setting, I need the number of trials, and those are a fixed number of trials ahead of time. X is equal to the number of successes out of n trials. I need a fixed probability P of success. And I also need independence. Now, if I am designing this defense system with the satellites, I'd like to ask this question. How many satellites should I expect to detect the missile? So that's a keyword, expect. So if I'm answering this question, I'm really asking you for E of x, which is the mean. And I'm going to use what that's mx prime of 0. And I'm going to compute the mean that way. So let's compute the moment generating function of a binomial. Okay. So I want to compute the moment generating function of binomial. That's going to be the expected value of e to the t times x, always. And this is going to be e to the tx times the probability of x, from x equals 0 to n. Okay. Now, before I proceed, I'm just going to write this fact down. That's a plus b to the n is going to be the summation from x equals 0 to n. Excuse me. Let me write one more thing down. And choose x times a to the x times b to the n minus x. Now, this should look familiar from your review, because this is the binomial theorem, and I asked you what this was on your review. Okay. Now let's continue this calculation. This is going to be the summation from x equals 0 to n e to the t times x. Fortunately, we know what the density function p of x is. The probability of x is going to be n choose x times q to the n minus x. Q is 1 minus p times p raised to the x power. Now, I'm going to group these two items together. And I'm going to have n choose x times q to the n minus x times p e to the t. They're both raised to the x power like that. Wait, now I think I can go ahead and use the binomial theorem here. That is what I'm going to call A. This is what I'm going to call B. And everything else looks good. So when I use this binomial, I'm going to get this. The binomial theorem is going to say that this is going to be p times e to the t plus q raised to the nth power. And if I want to take this derivative, well, that's just simple calculus. Bring the exponent down, p times e to the t plus q. I'll use the chain rule, so n minus 1. But now I have to multiply by the derivative of what's inside. The derivative of p to the t is p to the t. the derivative of q is 0, because it's constant. Okay. And this is the derivative, not evaluated at 0, so I'll put the q there. Now we're going to evaluate this at 0. So n times p e to the 0, e to the 0 is 1, so that's just p plus q raised to the n minus 1 power. That is just 1, times p e to the 0, so times p, and that's n times p. So in this example, for a binomial, e of x is just n times p. And in this case, n was 4, the probability of success was 0.9. So I'll do the multiply symbol like that, 0.9. So I think we're going to expect 3.6 satellites to detect the missile. You might also ask, hey, what's the variance? And you're going to calculate the variance. You might do it this way: e of x squared minus mu squared. Now, note mu is equal to n times p. We did that. And e of x squared, well, remember that's the moment generating function's second derivative evaluated at 0. And when you do this, I'll let you verify this. The variance of x is going to be n times p times q. And one last thing is that q is going to be 1 minus p. Okay, so that is the binomial distribution. And I want to reiterate, just like I did for the geometric, the most important thing about a binomial is being able to recognize the binomial distribution. Okay. So one key difference is that there's a finite number of trials. Unlike the geometric, in which there's an infinite number of trials. Now, it's not the only distribution with a finite number of trials. It requires a fixed probability, P, of success. And it needs independence. If you have all these things, then yes, you are good to use the binomial distribution, and then you can use this formula. So instead of write probability x equals k, I'll write probability x equals little x. That's a constant. This is the number of successes. Okay, and this will just be n choose little x times p to the x times q to the n minus x. So when you have all of those things listed on the last slide, you can go ahead and use this formula, which is the binomial distribution.